Is his presentation on there already?
Yes, I think so.
Okay. Oh, wonderful. Thank you. So there's no rest here. We're going to go right to the next keynote, and I think you're going to find this very stimulating. This whole concept of wireless power transfer is been something that we've seen in science fiction, but we now have some reality. So we are really honored to have Professor Chris Mee. He's the IEEE and SAE Fellow, a distinguished professor. I'm going to read his biography. Dr. Mee is a distinguished professor of electrical and computer engineering at San Diego State University. He's an IEEE Fellow and also a Fellow of the Society of Automotive Engineers. He's a director of the U.S. Department of Energy-funded Graduate Automotive Technology Education Center for Electric Drive Transportation at San Diego State University. He was previously a faculty member at the University of Michigan in Dearborn from 2001 to 2015, an electrical engineer with General Electric from 2000 to 2001. He served as the CTO of First Power Solutions from 2008 to 2011, and the CTO of EV Safe Charger, Inc. from 2021. He received his PhD from the University of Toronto in Canada in 2001. He's published 5 books, over 200 journal papers, 130 conference papers, and 20 issued and pending patents. And that's not counting his presentation today. He served as editor-in-chief of the area editor, guest editor, and associate editor of multiple IEEE transactions international journals, as well as a general chair of over 10 IEEE international conferences. He's won numerous awards, including the Distinguished Teaching Award, Distinguished Research Award from the University of Michigan, IEEE Region 4 Distinguished Engineer Award, IEEE Southeastern Michigan Section Outstanding Professional Award, and oh my goodness, on and on and on. We're not going to have time for his presentation, but I would commend you to take a look at his biography, which is published on our website. We are very pleased to have Dr. Mee here today to present.
Okay, good morning, everybody. It's a great pleasure to be here. To be honest with you, this is my first time to attend ICCE and also in the consumer technology activities. My main home society is power electronics, but that's why we call it IEEE, because we deal with all kinds of technology that are actually in the train. So today I will share with you. Okay, let me see if I can make this work. Oops. No. Oh, it's actually working. Oh, okay. It's actually working, yeah. So the title of my talk is Wireless Power Transfer from Science Fiction to Reality. Now, the reason I call this title because wireless power transfer has been over 100 years old technology, but only recently are we able to see this in applications from milliwatts to megawatts. There's a wide range of application for wireless power transfer. And my talk will include just a few sub areas. We're going to start with the question of why, what is it, why is it, why we do it, and how we do it. What is the history, and what is the basic principle? How does it? How do we how does the technology work? And then we're going to look at mostly the applications of wireless power in the different areas that are going to impact our lives. And I'm also going to discuss a little bit about safety of wireless power, because that's one very important topic when you deal with something that is wireless. So ideally, wireless power transfer is very similar to our wireless communication technology. If you look at our cell phones today, we basically carry it everywhere. But if you go back 30 years ago, cell phones was rare, and we all had landlines. But today, I think most of the homes and offices also do not have landlines anymore, or we all use cell phones. So cell phones receive and transmit signals through the air. It does not need any wire to connect the device to another device or to a central station. So wireless power transfer borrows the same idea. We want to set up a transmitter somewhere. It can transmit electricity through air, and over at another place, we're able to receive the power by using a receiving device, and we can utilize that energy to power any device that we wanted. Now, this is the ideal scenario. Like you can have one transmitter, you can have multiple receivers, you can have relay stations, just like our wireless towers, and you can have multiple devices, all kinds of devices, from low power to high power. But again, as I said, this is only ideal scenario. In today's scenario, actually, it is not possible yet, but you will see this wireless power brings to us a lot of advantages. Well, first of all, it provides a safe way to transmit electricity. Taking an electric vehicle charging as an example, in a cold winter with the snow and ice, it's very difficult to charge the vehicle when the handle is freezing cold. And at minus 20 degrees C, your hand might actually stick with the metal handle or plastic handle, then you might get hurt. Right? And also, if there's ice getting into the plug, you might get an electric shock. So all those concerns exist. But if we convert that into wireless power charging, we don't have to worry about it. We don't have to worry about the cable being stolen. We don't worry about the cable is worn or electric shock and things like that. Or second advantage I can think of is convenience. Nowadays, we all carry a lot of cables with us, and it's messy. When I go anywhere travel, I carry at least 5-6 different cables for my phones, my smartwatch, and my laptop, and so on. Right? And also in some other areas, you can see that is a picture that I took. You can see the mess. And also recently, you might also have heard that Los Angeles has a lot of, probably one of the hottest hit wildfire, and it burned also many tens of billions of dollars worth of property already. And but if you search YouTube, you can find some of the areas still use wire to transfer electricity, and the wire was so close to the trees. And when wind blows, the wire started to shake, and they catch the trees, and they produce fire. They ignite the trees, and that's how many of the fires start. Not the only reason, but wireless power, if it is possible, that can provide us with some safety and convenience. And lastly is productivity. In many applications, when you have these vehicles, for example, inside a factory, inside a warehouse, you cannot use diesel or gas vehicles. You have to use electricity powered vehicles. Many of them are autonomous vehicles. But these vehicles need to be charged, and the charging takes anywhere from 1 hour to 4 hours. So it's an interruption for productivity, and it can be costly to maintain these vehicles and to manage this operation of these vehicles. But if we convert these vehicles into wireless charge vehicles, you would dramatically increase productivity and also reduce maintenance, reduce operational cost. So there are many advantages doing wireless power. Now, of course, how do we do that? In fact, it's not that difficult. If you look at electric vehicle charging, simply you would get power from electrical supply, and then you bury this transmitter underground. On the vehicle side, you build a receiver. Once the vehicle is parked on top of the transmitter, you activate the transmitter, and the receiver started to receive power, and that power can be used to charge your battery. In a scenario where you have this vehicle driving dynamically on the road, you can pave many transmitters under the pavement. And the vehicle passes through each transmitter. The transmitter is activated, and the power is transmitted to the vehicle. So it's fairly simple. How, of course, in principle, it's simple, but it's not that easy to build that dynamic charging road given the cost and difficulty of construction. But going to the low power area, we already have pretty much all the newest cell phones have this wireless charging capability already. And if you open the phone, you'll find that it has a little antenna receiver inside. And that antenna is not the antenna we use to receive a signal, but it's actually to receive power. And if you buy this wireless charging device, it will have a transmitter inside. It got all the devices, controllers, communications. When the phone is put on top of the transmitter, and the phone gets charged. So the power is transmitted between the transmitter and receiver without any wire. And if you happen to put a keychain on top of the transmitter, it will detect it. It will stop transmitting. So therefore, you don't have to worry about the keychain being heated up or catching fire. So wireless power been very hot topic in the past 15 years. But if you go back in history, over 100 years ago, Nikola Tesla already started this idea of wireless power. And he spent a lot of time to validate his ideas, and he was able to build so-called Tesla coil. We still use it today. In fact, that's the principle we use for wireless power. There's a resonance circuit inside, and to cancel the leakage of transformers, and we would build either electrical or magnetic field, using that electrical magnetic field to transfer energy, and then the pickup device receives the field and convert that field energy into electrical energy that's being used by other devices. If you look on the right hand, on the second to the top, that is a tower used to be called Tesla Tower, and that's what he built again over 120 years ago. He wanted to use that to transfer electricity in New York City. Now, this project was very ambitious, but also very difficult. He was not successful in completing the project, and the investors lost patience, and they actually rushed to destroy the tower and sold the steel to recover their investment. But one of the crazy theory was that Tesla found some of Earth's vibration, and he was able to use that the device under the tower to capture that energy and amplify it, and then he can transfer that through that big antenna, like tower on top of the tower, and the energy can be transmitted. But that theory itself, whether true or not, we don't know, but that has been floating around for quite some time. And wireless power from the early 1900s until around 2010, nearly 100 years, there was not much of progress. But right around that time, and all of a sudden we see a lot of development, including my group and many others around the world, start to look at this. Actually, it is possible. And why we're not able to do it in the past? Well, it really turned out to be a lot of technology progress altogether made this happen. And for examples, including like power electronics, where we can switch now at megahertz frequency. But going back 20, 30 years ago, we could only switch around 10 to 20 kilohertz. Right? That's a huge progress. And looking at magnetic materials, looking at these wires and all that kind of stuff that we can use today, and looking at the microcontroller speed. Right? Earlier, from our previous talk, you can see that how much time he was able to reduce by building the avatars from hours to now seconds, right? And similarly, in power electronics, we're able to accelerate the control so that we can realize the kind of waveforms we need to realize the kind of power transfer we need. So today, really, the technology is quite mature, and we are still dealing with some issues, for example, size, that in particular with high power transfer, we're dealing with cost, and we're dealing with some standardizations, we're dealing with some foreign objects, some EMC issues, and so on. And so talking about wireless power, what kind of technology, what kind of principle that we use to build our system? In fact, it's not that a mystery. Wireless power transfer is realized through waveforms. That waveforms can be generated by using electromagnetic fields, or by radiations, or even by some induction, right? And then if you look a little further, in the waves area, you have radios, you have ultrasound lasers, and all kinds of waves that we can use. All of this can be used to realize wireless power. And of course, some of them are going to be good for one application, some of them are going to be good for another application. For example, the induction is mainly used for heating. The radiation or the waves based are mostly used for long distance and low power applications. But electromagnetic field based are mostly used for high power and for near field applications. And if you look at the whole picture, the wireless power involves many stages of circuit or system. Any power, wireless power still have to get power somewhere. So usually would get power from the outlet or a transformer. Somewhere you have this wire connected to your transmitter. Now between the electricity supply to the transmitter, we need multi-stages of power conversion. So initially we need to get the AC power supply into DC, because most or almost all of the power supply today are AC, whether 60 hertz or whether 50 hertz. We do see DC power supply is moving at a fast pace, but the percentage is very, very low today. So mostly we have to convert this AC into DC. And in that process, we have to do a power factor correction. So many of you probably have heard that concept. And from that, after that power factor correction, we need to control the DC fluctuations or DC levels so that we can control the actual power transferred. And then after that, we would transfer the power from DC into high frequency AC. Here, typically we're referring to about at least 30 to 80 kilohertz in the high power region, up to 6 megahertz for the cell phone charging, and up to the gigahertz for medical device charging. So there's a whole wide frequency band that we use for wireless power. And on the receiver side, of course, if you receive AC power, then you rectify into DC so that you can charge your battery, or you can use it to power the device directly. And in my group of research, we did a fundamental progress around 2011 when we developed this power electronic circuit. We call this double-sided LCC. The reason we call this double-sided LCC is because if you look at the input side, after the bridge, we have this L, and then we have two Cs, and one C is used LCF1. CF1 was used for the resonant front end, and then we have C1 and L1 that forms a resonant circuit. So I'm not going to go into too much detail in the circuit. Many of you in the consumer electronics probably also know that we use the resonant circuit to increase the current and voltage in the transmitter device, so that the magnetic field built between the transmitter and receiver can cancel the leakage inductance, so that we can get high efficiency. How high we can get? Well, before the 2011, if we go back to before 2000, many people have built some devices. Efficiency rarely exceeded 50%. In 2008, for example, MIT built this huge device. They were able to transfer power at the efficiency roughly 25%. And then by 2010, there were a lot of progress made, and efficiency went up from that 25 to 50%, all the way to 85%, but still way below our expectations, especially for high power, because if you're looking at, let's say, 10 kilowatts charger, 85% means 1.5 kilowatts, a lot of heat to dissipate. So we did this design with double CC topology. We're able to increase the efficiency from roughly 85% at the time to about 95%. And if you look at this experimental results on the top, they were able to reach almost 96% at the full power of 8 kilowatts. That was done around 2012 to 2013. And after that, we also look at, so the previous, this one was done with inductive power transfer, which means it's based on magnetic field. So we use a coil to build a magnetic field, and our pickup system pick up energy from the magnetic field. But then we realized that there is also an analogy between electrical and the magnetic field, electrical field, right? So we want to see whether we can also transfer power using electrical field. And then we did this dramatic experiment. This was done around 2015 to 2016 timeframe. And similarly, before that time, people was already able to use capacitive wireless power transfer or electrical field wireless power transfer at a power level roughly 5 to 10 watts. And that was very low power. By improving the circuit design, by increasing the frequency, and also increasing the voltage at the coupler, we were able to increase the power transfer from roughly a few watts to 2.4 kilowatts. That was an increase order of like 1,000. And that was a dramatic progress made at the time. As you can see, we have input, output, and we have the gate driver signals. And on the picture, you see those plates. That was a transmitter and receiver that can be used, for example, on a vehicle to receive power to charge electric vehicles. Now, wireless power transfer has come to the point, well, it's a prime time for commercialization. But it turned out that it's been a little bit slower than we have expected, especially in high-power wireless power applications. And the reason is very simple. The cost, the size, the interference, the safety, and the interoperability, and all that plays some picture. Now, for consumer electronics, consumer devices, that would be much quicker because that generally seems to be easier to standardize. For example, we have USB-A, USB-B, USB-C today. That's been most popular now. Earlier, we have CDs and we have hard drives that all use the same protocol. That hard drive can be formatted by any computer or any system that can be used, right? And then today, wireless power charging already been standardized for iPhones, iPads. They all use the same protocol, same communication protocol, and the same technology. But for high power, this is what I want to focus today in the next few slides, is very difficult. Now, the application extends from vehicle charging. For example, you're looking at passenger cars, you're looking at buses, trucks, and so on. And also, you can expect to see dynamic charging and stationary charging. So stationary means that your vehicle is parked and charged. Dynamic means your vehicle is being driven on the road and it's being charged while the vehicle is driven. And that is more difficult to do because of cost again. But over the world, around the world, we already see at least nearly 20 demonstration projects. Some of them extend to many miles of operations. So it's been done. It's a matter of whether we can make this efficient, we can make this cost effective. But in between now and the future, where the technology is being fully commercialized, we are going to see some niche applications such as these buses. And if you notice that in many of the countries, especially in China, they have been banning the use of gasoline or diesel-powered buses. Everything was converted to electric. But these buses are running hundreds of miles a day, not like a passenger car doing 40 or 50 miles a day, but this has been doing hundreds of miles. With that many miles on the vehicle, you need a lot of batteries. So it turned out each bus usually carries around 3 tons to 4 tons of battery, including the batteries, the casing, and all the auxiliary devices. Just the battery system, 3 to 4 tons. That is a lot of weight to carry around. Not to mention that there's a lot of money to invest to buy the battery, right? So if we convert these buses into wireless charging vehicle, we can dramatically reduce the batteries needed for the vehicle. You don't have to build the whole city with wireless power, but you only need to build these charge stations at bus stops. And each bus stop can be built such as 20 to 30, 50 meters. The bus being charged was slowly driven into the station and out the station when people getting on and off the bus. You can reduce the cost of the bus, reduce the weight of the bus, therefore increase energy efficiency, right? And applications like this one on a ship, electrical ship, it's like ships are not popular yet, but that's something that we can do. Applications like AGVs in part of Los Angeles, for example. A lot of smell because of diesel buses running there, but they don't want to replace with EV because why? EVs are much more expensive and they need to charge the vehicle for many hours. So therefore, replacing one diesel vehicle, they need 2 electric vehicles. And one vehicle is 2 to 3 times more expensive than a diesel vehicle. So therefore, by replacing one diesel vehicle, they need to invest 4 to 8 times the cost to replace one. And they're not going to do it because they will never be able to recover the investment. So how do you convince them to convert into electric? Again, wireless power. Because you can charge this vehicle wirelessly, so they don't have to buy 2 vehicles to replace one. Now you reduce the battery use on the vehicle, therefore the cost will be much less. They don't have to invest a lot of money. If the cities and government can help build the wireless charging system and they only invest in the vehicle, right? They can, because electricity is much cheaper than diesel and gas, right? So they can recover the investment within a matter of a year or 2. And if you can do this, they will be very happy. So this is a very dramatic development. There are many other applications I can talk about. For example, in the underwater vehicle, if you have to charge this underwater robots, it's very difficult because many of them running at deep sea. So the charging socket has to be sealed, and they have to come down up, and they have to come up to the shore, or they come up to the ship to charge them. So you can charge them down under the water, it will dramatically increase their productivity. And another example, if you ever go near a high-rise building, you might wonder why there are so many cables hanging there, right? Because they have to transfer electricity to inside the cable car. And then those cables becomes the weakest point, and they also increase the losses. But if we can convert this vehicle like in the middle diagram, we transfer power. It doesn't not necessarily have to charge, but simply transfer power through a wireless system, and then the cable car inside the cart that you don't need a like flip-flop cable anymore. Devices like this one under the mining area is very important because you cannot plug something under the coal mining area because that's going to induce explosion because the gas inside. But so the people have to carry tools up and down to charge them, and they have to carry more because each tool only lasts about an hour and 2, right? So if they want to work 8-hour shift, they have to carry 4 pair of tools into the underground mining. But if you can charge them underground, they only need 2 pairs, so that one is being used, the other is being charged. So this is very important. Now coming down, I know there's a lot of discussion also yesterday, the medical devices. Things like this inside the body with a pacemaker. The pacemaker lasts many years now. Initially in the 1960s when they invested this pacemaker, the battery only lasted a few months. And the first person actually got the pacemaker only lived about 9 or 11 months. And the people don't usually live very long with the pacemaker in the beginning, or the pacemaker was first invented. But nowadays, people can live very long. I have known one person, she is almost 85, 86 years old, and she had the pacemaker for 20 years already. But of course, it's not the same pacemaker, it's been replaced twice already. Very painful. Now, if we can charge this device inside the body without doing the operation, it will be really, really cool, right? And of course, medical device is not just a pacemaker, but you're looking at the brain stimulators, you're looking at like blind people, eyeglasses, all this, they involve like Tesla, like Elon Musk's, the brain stuff. All of them need batteries. With that high computational power needed, like image processing, pacemaker is actually not that bad because pacemaker they don't consume any power for computation. They only generate little pulse, right? So the power consumption is very low. But going to process language, process image, you need a lot of computational power, which consumes a lot of energy. Therefore, the battery is a problem. You cannot put a big battery inside the brain because there's not a lot of space there, right? So I think eventually this will have to be wireless powered. And now, of course, you can think about other applications, the drones, for example. Drones, most of the drones today, except for military drones, most of the drones electrical, they only last about 30 minutes, most of them. Some of them may be even shorter. Some of them may be a little bit longer, but most of them are around 30 minutes. They cannot do a lot of tasks because of the short time frame. Now, how do you increase the operation time? Well, one of the ways is to charge them wirelessly, whether they can be charged on a platform or they can be charged while they're flying. Of course, that's going to be super difficult, right? But it's something we can dream for, and it might happen. Who knows? And lastly, I want to just give you an example of this dramatic, like space-based wireless power. Now, on the satellite, for example, you have solar panels, and you might also have nuclear batteries. But one of the problems is that if some of the satellite carries like robots that work with the satellite, like to fix things like that, but this robot's little battery won't last very long. Once it's used, those little things become space garbage. If we can build a wireless powered robot, and they can work much longer. So that's something you can dream of maybe in the future. Now, there's also concept that's been developed recently. Of course, this is going to be, whether it's going to work, we don't know. But as scientists, we always have to wonder. We have to always to explore. The idea is that we have solar panels already on the ground. The problem is that the solar panels don't generate at night, and they don't generate when there's a rain and a cloud. If you move the solar panels up in the space, they can generate 24/7, all year long. Maybe only 2 to 3 days darkness they don't generate. They can generate, the intensity is much higher, so the same solar panel can generate almost 10 times power as it is on the ground. But the problem is, how do you get the power to the ground? It would be ridiculous to hang a cable from 10 miles top, in the space and to the ground. It's just not realistic. So people say, well, let's transfer them to the ground with wireless power. Just like the sun, right? You use that, you connect energy, and then you shine a laser or microwave on the ground. You get this receiver on the ground, then you can convert that energy back into electricity, and then you can power the world. Very simple. You need only about a mile square to power the whole city, like Los Angeles. Right? So, again, that's a story. Good. And then, of course, experiment has been done. One of the researchers at University of Southern California worked with a satellite company. They shot this rocket and with this solar generation, with the transmitter device in space, and they were able to detect energy on the ground. So that was a huge progress. But next, let me talk about the safety of wireless power, because you can imagine If you have a high-power device, well, you could have humans, animals, metals all around. And we know that humans can be susceptible to magnetic and electric field. Well, fortunately, we already have standards to let us know how much magnetic field and how much electric field is safe. In this example, I put the standards in the yellow block. You can see 227 microtesla and so on, with pacemaker a little lower. And then we simulate this system to see how much is the magnetic field or the electric field. It turned out that the magnetic field is very low, much lower than the standards. Electric field, same thing, almost like 40 times lower than the standard. So I think it's safe. People sitting in the vehicle, similarly, it's very safe because electrical magnetic field doesn't usually get into a metal shield. It becomes a shielding device. The problem only happens when an animal gets into the on top of a transmitter, and the electrode goes to millitesla at hundreds of kilohertz. That can generate enough heat inside the animal to reach the temperature, something from like a normal temperature to more than 40 to 45 degrees C. You can imagine the animal will probably going to be killed. Lastly, is that if you have metals, we know that metal is going to generate eddy current. If you have metal on top of the transmitter with a strong magnetic field in the millitesla and the hundreds of kilohertz, temperature is going to rise. And we did experiment. If we have a bolt, and the bolt temperature will increase about 15 degrees C per minute, 15 degrees per minute. So within about 10 minutes, you got almost like 150 degrees C. Within 20 minutes, it's going to ignite paper and other combustible things like papers around it. So in a nutshell, we need to be careful. We need to be able to detect metals. We need to be able to detect animals so that we don't hurt animals. We need to detect metals so that we don't induce fire. So when you charge your cell phone, even though it has a detection system, make sure you don't put metals on your transmitter, because if it's a fault, you might actually catch fire. Okay, but consumer electronics have been more really in terms of standardization. That's why you see that in your daily life. But for high power, it's very difficult to standardize it. Like you can imagine that if you drive a GM vehicle or Toyota vehicle, you want to be able to charge at the same charger, right? So that's very difficult to do. There's some standards are going, but it's very slow. And so interoperability and that is going to be really a issue. So the final words is that WPT is an enabling technology. It's been ever since huge progress in the past 15 years and still evolving. The niche is that we need, especially for high power, we need to find applications where it's going to help either increase safety, increase productivity, reduce cost, saving energy, all that kind of good stuff you can get out of this wireless power. That's where we're going to see applications and commercialization. But if you want to dream what Tesla has dreamed over 100 years ago, well, we can get energy anywhere from the air. That's not going to happen. Dreaming of not carrying a cable around with you, that's not going to happen very soon. I can't say it's not going to happen, but it's not going to happen soon, right? So with that, I want to thank you all for your attention, and I'll be happy if there's any time for questions.
Well, thank you, Dr. B. We have some time for some questions. Anybody have a question or comment or something that's in there? This is my phone is always running down, so
good exercise for you.
I'd like to be able to charge it while I'm walking around the room here, but I don't think I'll be in the near field of anything.
Yeah, I have two questions. So the first is that the concept of the bus charging, intermediate charge, it certainly makes sense, would reduce costs for continuous. But doesn't that decrease the battery life significantly by having short charges rather than one long charge and drain down one large charge?
Yes, very good question. In fact, it depends on most of the battery degradation happens when you have a fast charge, and you have a fully charged or discharged battery. I didn't have time to go through. I do a lot of battery research. Like here, for example, we build the stations and we build this battery testing, model and testing. When you charge the battery at more than 1C, it degrades the battery very quickly. Or when you fully charge the battery, it also degrades very quickly. But when you shallow charge the battery, like between 40 to 60% or 70%, in the middle range, when you charge the battery at a much slower rate, like let's say less than 1C at the shallow range, the battery can last tens of thousands of cycles.
Yeah, I'm aware of that. Yeah, that's true. The shorter charge.
Yeah.
Yeah. Last question is that your last example with the heavy charging and the gum wrapper. I certainly wouldn't want anybody with a pacemaker to be near your charging station. So there is a big safety issue.
You are absolutely right. However, you see that metal and also the animal that was directly on top of the transmitter. If you happen to be around the charging, like the car charging, the car is charging, you're around the car, you're absolutely safe, whatever metal device you have in your body.
Well, you got time for one more question before the break. Yep, yes, sir.
Thank you very much. Okay, first of all, thank you very much for your interesting talk. I was wondering if this application can benefit railway, substituting aerial power lines.
Can you repeat what?
Yes, sorry. I was wondering if this technology can benefit railways.
Railway trains. Not a lot. I can tell you, because trains today we use a pantograph, and it's very reliable and very safe, and most importantly, it's a lot cheaper to build. For trains, the power is not in the kilowatts, it's actually in the tens of megawatts. So it's very high power. And also trains travel at a very fast speed. So the system, to build the system can cost you a fortune. However, people are talking about this scenario. I can give you, you can see how this can be utilized. For trains, especially fast train, right? We run the trains around under many tunnels. And to accommodate the pantograph in the tunnel, we have to dig a big tunnel. And the cost is tremendous, right? So people talk about inside tunnels, we don't use the pantograph, actually switch them to wireless power. So that we build a smaller tunnel, right? So the cost to build tunnel is very, very big, right? So before the train goes into the tunnel, they just switch over to this wireless power on the track instead of on top of the pantograph. And therefore, you can reduce dramatically the cost to build the tunnel, and the savings would catch much more than you can spend on building the wireless power. So that's one scenario that you can see.
Thank you very much.
Yeah.
So thank you very much. I think we're out of time. We probably didn't run out of questions, but let's give Dr. B a hand again.
Yeah.
Put up the next slide.
Thank you very much, Chris. This is a certificate of your excellent keynote. Thank you very much. Thank you, Chipe. Thank you very much. Thank you.
Okay, everyone. So you can see up here on the screen, we have a break scheduled till 1:15. We're cutting into it just a little bit. The food is next door, but we are starting the panel promptly at 10:45. So I would ask you to get your food and please come